Hello guys, this is the first video where we're going to start talking about the next module, and the next module on the item is, of course, after doing the arm, of course, is the leg. So when we were working on the arm, I took a chance to start introducing encapsulation of functions to get much more powerful solvers. And although those folders, they seem complicated, they still are at the base or at the foundation of what can be achieved in terms of functionality on a module such an arm or a leg or a spine or whatever you can think of. Now today we're going to start talking about the leg, and at the end, of course, we're going to implement a leg module. Although I'm going to start before we jump and build a module, that is not going to happen in this video. I'm using this video as a chance to start introducing a few more concepts, something that will allow us to both rig the leg and improve our solvers that we've built so far to be a little bit more versatile. So the first, of course, the leg right now, it's a very simple leg. It's just a thigh, a calf, a foot, and a ball. The features on this leg, let me reset that. The features on this leg are, we want IK and FK switch and matching, and then we want something that I saw people calling reverse foot. And just a fun, quick story. The reverse foot is actually something that comes from not really the setup that today it's named reverse foot, but at the very beginning, a long time ago, the reverse foot was achieved by literally reversing the joints on the foot, like going from here to here, so the hierarchy was completely reversed. But then with the introduction of more solvers and constraining, this is not necessary anymore. So the reverse foot is actually achieved by being smart about parenting controls that are driving the bones, so the bones can be completely, in the way you expect them to be. But then, and we don't need to add any additional intermediate reverse foot joints in order to achieve what a reverse foot is, because FK is fairly straightforward. We want a control basically per bone, where we are able to rotate as if this was a skeleton, like that, exactly like this. When it comes to IK, instead, what we want is being able to lift the leg, the foot, up by a completely different pivot. That could be here, or on the back. In this case, I'm not going to start implementing this now, but we are definitely going to use the what I call the smart hierarchy among controls, and it's what today is known as reverse foot, even though to be precise, that's not the origin of it, but it's fine. So in this first video, rather than building the leg, I want to start introducing something that is called projection of parent, and which basically it's kind of a way to dynamically change the hierarchical relationship of something driven by something. We covered this in the very first video of this series, when I was showing in Maya the direct way, or the constraint way, or the hierarchy way to move things, to create a relationship between one transform and another transform. Now, why is that now becoming a little bit more important, that concept? Well, so far, up till now, what we really did in our solvers or modules is to dynamically align the control to the bones. And then by moving the control that is perfectly aligned with the bone, we were able to get a predictable behavior. And most of the time that's fine, but there are certain scenarios where you cannot do that, and the foot is one of them. Also, what I'm saying, it's true in most of cases, especially for bipeds, but it's not always true. There are rigs that do require that the bone, the control in this case, that is at the foot, is aligned perfectly to the bone. Now let's see what I mean by that. So this bone here, the red one, this control here, the red one, is perfectly aligned like all our other controls to the bones, which means when I move it up and down, it moves along the bone. And what happens is that if I use this bone here, which is called control A, which is perfectly aligned to the bone, when I move it, everything it's fine, right? So we don't see any popping or anything because the bone is perfectly aligned. I can direct connect this transform to this transform, and being them expressed in wall space, this works perfectly. Now the problem with the foot is that usually the foot, you don't want to have this kind of control aligned to the bone, but rather to the floor or the world. So, and this is because the up and down movement, if you move it up and down here like that, the bone goes up this way. When on something like that, especially for a walk cycle, to have a really clean animation graph, it's better to actually have the control go up only on one axis. So the up movement is truly the world up. And this has to do with the way, you can interpret the animation graph through visually. The animator can see curves going up and down and perfectly realize that this is an up and down movement. So how do we do that though? Like if so far we have been seeing controls being perfectly oriented to the bones, if the bones has some sort of orientation, this becomes impossible. Well, of course it's not impossible. So how do we do it? So we saw this example. Control A is moving foot L because it's perfectly aligned, and this is what I call a direct connection, right? This is one way of driving things. Then we saw that if I were to switch this bone with Control B, you can see that something happens. Now, Control B, being the blue one, being aligned to the world, is now basically transferring all this data, and the bone does not work anymore. And if I move this up and down, this moves up and down, but the bone is completely flipped. It's rotated as well because it's a direct connection. So I still want to be able to keep the bone this way with an offset, but still being able to drive that bone with this control. So when we were looking through solvers, we saw one way of moving things in a different space. And one of these ways is using the transform constraint. And I want to point out the color coding here. So this is a purple node and this is a black node. And I believe that these are, I don't know exactly what purple means, but from what I see, the type of nodes that have this color are more like closer to a solver. It's kind of a complex algorithm, which to me it's more heavy in terms of computation. Now I don't know what the color means exactly, but I've noticed that that's the kind of things, the vibes I'm getting when I'm creating this kind of solvers. So the transform constraints, if I detach this and connect this to that by keeping maintain offset on, it does exactly what we expect. So this will be enough, right? Well, this works, although I'm not really happy about this. And the reason is transform constraint to me sounds like, and again, please, I may be wrong, but sounds like this node per se, it's a bit more heavy than what I'm about to show. Also, transform constraint, it's a quick way to, I think this is better used when you have to blend between the position of different transforms, like we saw in one example in the past. Okay. Then the third node is something called ProjectToNewParent, and if we hover over it, it says it projects your child from a previous to a new parent. So you're basically, even if you're not changing the hierarchy, you're expressing the value as if you're outputting the value as if this transform was in your hierarchy. What basically that means is that you are changing the parent-child relationship by, instead of doing that physically in the hierarchy, you're doing that through a multiplication of matrix that is taking care into this node. All right. So what that means is that instead of using this node, I can use this node. And I know this is a bit, this is my interpretation, but I really believe that this node is way faster than this one. So the way this works is that you would specify, you know, control B here, if this is the control B saying, okay, this is the old parent, so itself, but this is the new parent. So you wanna specify, and you can see it here. So if you want the pelvis to move with the head, you can set the child initial, set the old parent to be the head initial, and set the new parent the head as well, because not initial equals current. What this means is that basically you're trying to express the new space of this control or bone or whatever through this new space. So you're actually, I know it looks like I'm reading, but you're projecting this transform to a new parent. So now what you can do is take the foot, set the transform, delete that, and let's execute that. So at the beginning I was a bit confused, but the more I've used, the more this makes sense. It looks like I'm repeating a lot of information here. Control B, foot L, all right? But what this is just computing a matrix based on certain spaces. It does not do anything. It is still not connected to anything. This internally is just saying, give me the values as if this was child of that. It's not, you don't have to connect these two things together if you don't want to. Most of the time, that's what you want to do. You want to drive this in a different space. But this is literally a node that computes a transform output based on a different input space. These are on different parent. So if I were to connect this to that now and compile, I would get the exact same behavior. But the difference is now that when I move Z up, only Z moves up and only Z changes. So you can see that this node here is quite powerful because it allows us to do exactly what we did so far, but without restricting us to the orientation of the bones. Now, this is my this is something I think what I'm about to say is true based on guessing and a bit of experience. In terms of performance here, I think this is the fastest. Then immediately after that you have this, and immediately after that you have this. So with this in mind, it means that we can improve our solvers to reflect this in case we want this new option, if we don't want the controls to be aligned to the bones, like in this case. And same can go with the pelvis. You want the pelvis to go up and down, not along the spine. Unless it's a very weird character, but let's say for a biped, you really want the pelvis to be, even if the bone in the spine it's rotated and it follows all the spine bones like a curve, but you want the control, the main control to be up and down, and this is another example of that. So I'm sorry we didn't touch much of the leg, but I think this was a good time to speak about ProjectToNewParent. Cheers.